Okay, so now that we've been dealing with the special relativity definitions, let's also now introduce, maybe again, the concept of space-time diagrams. Thank you, 𝘍𝘂𝘐𝑬𝘵, for that. And see how we can understand them and what they tell us and this concept of world lines. So, in part A, we want to draw a space-time diagram representing the game of catch, or conversation, between two people at rest. They're 10 feet apart. How is it possible for them to communicate given that their separation is space-like? Okay, so remember what space-like means. And then part B, there's an old limerick that runs as follows. There once was a girl named Miss Bright, who could travel much faster than light. She departed one day the Einsteinian way and returned the previous night. What do you think? Even if she could travel faster than light, could she return before she sets out? Could she arrive at the same intermediate destination before she set out? And draw a space-time diagram representing this trip. Alright, so let's talk about how we start with this. So, in part A, truth is you never do communicate with the other person right now. You communicate with the person he or she will be when the message gets there. Okay, that makes sense because it takes time for the message to send. And the response comes back to an older and wiser you. Okay, we'll draw that out in a second. Now, for B, there's no way that this holds. It is true that a moving observer might say she arrived at B before she left A, but for the round trip, everyone must agree that she arrives back after she set out. Okay, let's go ahead and draw out what we see here. So, in the space-time diagrams, we have CT on the vertical and a position on the horizontal. And if we're playing catch, or communicating, we see that the world line of the ball is bouncing back and forth when we have a distance of 10 feet in between us. So the world line of player 1 and the world line of player 2 are the strict bounds that we have. And we set this space-like because the bounds run perpendicular to the x-axis. Cool, we like that. So we send a message, it takes time to get there. It takes CT to get there, actually. That's how fast it can get there. Then we take a little time adjusting it, and then we send it back. But again, we have to move up the world lines every time in order for the conversation to happen. Pretty cool. Now, for this person, we see that we have a line here where x is equal to CT. That is the max boundary points that we could have. And this is where the light cone comes in. But we see that in order for A to get to B, and for B to get back to C, we still have to progress forward on CT. So there's no way that we could get from A to B and back to A without progressing forward. It's a little bit tricky to deal with some of these things, and again, it's really fun when we can kind of conceptualize these breaks, but overall, man, relativity is really freaking cool.